Let's complete this part with what, for mathematical reasons, should not be done within the blockchain. For purely mathematical, not technological reasons, we've seen that the things that must be done must result in a deterministic outcome. Okay. If I say, write a secret random number, it's clear that the consistency won't be possible. All that is related to with lack of precision or randomness must be avoided. There are instruments can be provided to avoid this, and these instruments use a host function which does the work for you. So if you need a random number, ask it to the core, and the core will give you a random number, but it won't give you in the same way as if you had inserted rand. You know that the conception of random doesn't exist in the computer. So how can random work in a computer? It works with a seed, after which I have an f of the seed, which gives me a random number. After which, this f, what does it do fundamentally? If you're asked to write the function rand, it wouldn't take any parameter inside. It would say let n be equal to the hash of seed, which is this. At this point, I obtain another random number. I do a return. N, before I do the return n, I do seed equals n. In this way, what happens? The first time I ask a random number, it parts from the seed, it does a hash, which gives a value which might not be return n, but might be return n dot to number, which converts a hash into a number. The important thing is that it takes the return value and returns it to seed. So that if I launch it several times, so that I get a random number every time. If this thing is managed by the core guarantees that all nodes have the same seed. And every time these nodes call up the random function, they contaminate the seed in exactly the same way. So, if I call up the rand within the function, every programming language and every core has its own way of doing rand, which maybe inserts the time, and time varies between computers. I can never achieve an internal consistency between the random numbers. The same thing goes for the dates. For the dates, we just have to add one more thing. Other elements come into play. Network latency and speed of light. If I have a node in Singapore, and this is a node in San Francisco, technically, I can try and achieve with nuclear force the synchronicity between these two nodes. I can have the same clock on the same computers, but at some time this node produces a transaction which it takes to San Francisco. I produce it at time 0, it arrives in San Francisco at time t1. If this node in t0 has taken into consideration the time when the transaction arrives in San Francisco, San Francisco will take the time into consideration differently to Singapore, because some seconds have passed to move the transaction from a place to another. So it's completely useless to synchronize the clocks when in reality there's a latency time involved. So I can say, I'll take into account the latency time. So I say, I put my clock 5 seconds ahead, but then there's the problem the other way. So the network traffic is even changes within microseconds. Another consideration, this happened some time ago. A boy said, if I want to consider microseconds, I think about rounding errors. Take into account, say, an hour. You don't see this problem anymore, but it's not true. The hour is a defined element. If this is the hour, if it happens here, I'd still have the same great problem. There's a time before and a time after. So it's not this that we can solve the problem with the time. We've corrected it in another way, which does fundamentally what we saw before with the Byzantine nodes. Every validator node proposes a time. It proposes a time between transactions. So for him, it's 11, here it's 11 o'clock and 1 minute, it's 11 and 3 minutes. These times end up in a block because they are real transactions. Or they go or they don't go. The moment they're in the block, everybody can take the average of these 3 times and update the smart contract, which is within every node, with the new time. It'll be 11 and 1 minute. But what happens? This can't happen every second. It happens every time the bootstrap is written. Let's say it takes place every hour. When the application asks the smart contract, what time is it? It'll say it's 11 and 1 minute, and in 10 minutes, 11 and 1 minute. It's not a time that travels around, it's a fixed time which moves in steps. This comes from an important mathematician. If you know Alice in Wonderland by Lewis Carroll, which wasn't his real name, Lewis Carroll wrote a story. There's a lot of mathematics in his stories. The paradox of the watch. If you remember the Mad Hatter and the rabbit that's always late, there's a scene in which we ask whether a stopped watch is more accurate than a watch that loses a second every day. In reality, the watch that loses a second every day is precise every 86,000 days. A stopwatch is precise twice a day. So it's a paradox, but it makes you understand that something that is slightly imprecise can be much more imprecise than something that's broken. So we've reproduced broken watches within the blockchain, which correct themselves. They should be stopped, and they must be stopped, because if they move, they become more imprecise. So the time which you go to read within the blockchain is a time in steps. So it's not clear that it changes every hour. It could change every minute or every day, but it doesn't matter. When it moves, it organizes itself. So if you go to build a time with an expiry, we need to take this into account, that moving once a month is a bit dangerous. For a motif of traffic, the algorithm that we are currently improving to understand how many people ask the time, if there's a great frequency of asking the time, almost continuous, clearly we need to increase the frequency in which the nodes send the time they have. Otherwise, the thing can go more slowly to a certain extent. But these are all adjustments that we are doing in fine-tuning. That doesn't mean it doesn't work, but we can improve them greatly. The fact is, knowing the time depends on who asks it. If you ask the blockchain, it gives you the information, what time, what day it is, but you need to take this into account. This phenomenon of scattering, it's an aspect that permits you to use the elements of expiry and voting. We've done some important voting recently. In these months, we organised an important national vote, and clearly it finishes at a certain time. When the voting finishes, no one can push from outside to change the time. Otherwise, if we don't turn it off, it can go ahead. Can I violate the rules of the voting? If you say we vote till midnight and I forgot to turn off, or I turn off earlier, maybe because I'm winning, I stop the vote earlier. This is not the blockchain. The blockchain does it on its own. My hands don't touch it. That's because in this context, the system sees there's an expiry date soon, near to midnight. So the system begins to update the time with a greater frequency as midnight approaches, when nobody cares about the time.